Hello. Today we're going to discuss matrices and matrix multiplication from the perspective of graphs and networks. One common way matrices arise is representation of relations between objects and/or concepts. We'll start with the simplest case of a one-to-one relationship. Here we see a graph which captures the relationship between methods of movement and animal types, namely that among birds, cats, and fish, and perhaps with the occasional exception, the only one which flies as its primary movement method is a bird, the only one which runs as its primary method of movement is a cat, and the only one which swims as its primary method of movement is a fish. An alternate way to visually capture the data is in a tabular fashion, where our rows are labeled by the available movement methods and columns are labeled by the available animals. To notate the edge from flies to bird, we place a 1 in the corresponding flies row and bird column. Likewise, an edge from runs to cat contributes a 1 in the runs row and cat column. And finally, the edge from swims to fish contributes a final 1 in the swims row and fish column. The rest of the entries are left empty, implicitly filled with a value of 0, to denote that there is no edge between the corresponding row vertex and column vertex. Now we expand our original graph to include a new attribute, fur, and a new animal type, bat, along with new edges pairing flies with bat and fur with both cat and bat. Our new array contains the same info as the previous example, but also contains new non-diagonal entries to capture our new edges. These tables are typically called matrices, the plural of the term matrix, or arrays. Now let's consider the following graph relating foods to associated nutrition info. While we could capture the graph in the same way by using 1 to denote the presence of an edge and 0, or simply empty, to denote the non-existence of an edge. In this example, we're going to use our edges to indicate some meaningful measurements. How many calories does a serving of each food have? How many grams of fat or sugar are in each serving of these foods? What's the cost of each? Instead of only using 1 to denote a relationship, we can instead use the actual weight of our edges. Moreover, if we know how many servings of each food item we can have, we can then use this data in our array to calculate the total calories, total fat, and sugar contents, and the total cost associated with our meal. This calculation is an example of vector matrix multiplication. We can represent this by placing a row vector on the left-hand side of our matrix, which tells us how many servings of each food item we have. To calculate the total number of calories in our meal, we must look at the values in the calories column and match the entries with those in our row vector. In this case, we have half an apple contributing 0.5 times 95 calories, and 2 eggs contributing 2 times 72 calories, giving a total of 191.5 calories, which we store in a new row vector. Observe that water had no corresponding term. There are two phenomena occurring here. Implicitly, the water calories entry has a value of 0. Multiplying 0 by any number returns 0, or in other words, 0 is a multiplicative annihilator. Adding 0 to any quantity doesn't change that quantity. In other words, 0 is an additive identity. What this means more generally is that when we're matching the entries of a row vector with the entries of a column vector, any pairs involving empty or 0 entries contribute nothing to the resulting sum of products. We see this again when calculating the fat content of our meal, in which the only term is that of the 2 eggs. Similarly, the only contributor to the amount of sugar in our meal is our half an apple. In contrast, every entry in our cost column is non-zero, so our sum has 3 terms, 1 coming from each food type. What if instead of a single meal, we had several of varying quantities of each food type? By restricting our view to each individual meal, we can perform vector matrix multiplication to find the nutrition info associated with that meal. Thus, to get the nutrition info for meal A, we would multiply the meal A row by our food nutrition matrix, producing a row labeled meal A, providing just its nutrition info. The same can be done for the remaining rows of our meal food matrix, contributing 2 more rows in our meal nutrition matrix. The result of this process, called matrix-matrix multiplication, is the product of our meal food and food nutrition matrices, a meal nutrition matrix. Observe that the row labels of our product are the row labels of our first matrix, and the column labels are the column labels of our second matrix. Moreover, the column labels of the first matrix match the row labels of our second matrix. If these did not overlap, the resulting matrix would simply be empty. In our previous examples of vector matrix and matrix-matrix multiplication, The entries of the resulting product reach a sum of the products of pairs of corresponding entries. In particular, our operations were taken with respect to real number addition and real number multiplication. However, there are scenarios in which other choices of operations might be more appropriate. Consider a network consisting of 4 nodes labeled Node A, Node B, Node C, and Node D, with the network topology represented either as a directed graph to the right or as a balanced bipartite graph as on the left. Each connection or link between two nodes has an associated bandwidth, which we can store in an array whose rows and columns are labeled by the nodes in our network. For each node, there is an implicit self-link with infinite bandwidth, giving our diagonal entries. The non-existence of connection between two nodes is equivalent to there being a link with 0 bandwidth. Our array represents the bandwidth between two nodes by following only a single link. What if we allow ourselves to follow up to 2 links in our transversal of the network? For example, although there is no link connecting node A to node D directly, we could follow 2 links passing through node C. The bandwidth of this path will be the minimum of the bandwidths of each individual link. In some circumstances, there might be multiple ways to go from one node to another, in which case we'll take the path which maximizes the bandwidth. That we're using operations other than the usual real number addition and multiplication means that we're not working with matrices in the traditional sense, but instead objects called associative arrays, which generalize matrices and allow for alternate data types and operations. This is the reason why we label this operation associative array multiplication instead of matrix multiplication. For example, there are 2 ways to go from node A back to itself in at most 2 steps. Either we stay at node A, or we go to node B and then back. The bandwidth of staying at node A is infinity, while the bandwidth of passing through node B is 10 megabits per second, since each link has a bandwidth of 10 megabits per second. The larger these 2 net bandwidths is infinity, so that's what we're going to put in the corresponding entry of our new associative array. To go from node A to node B, our only option is to use the link from node A to node B. Whether we consider ourselves as staying at node A for our first step before going to node B, or we're going to node B as our first step and then staying at node B, the bandwidth is the same, 10 megabits per second. From node A to node C, there's a unique path passing through node B. The link from A to B has a bandwidth of 10 megabits per second, while the link from B to C has a bandwidth of 5 megabits per second. So the path has a net bandwidth of 5 megabits per second, the minimum of the 2. Similarly, there's a unique path from node A to node D given by passing through node B. From A to B, our bandwidth is 10 megabits per second, and from B to D, our bandwidth is 12 megabits per second. So our net bandwidth is the minimum of the 2, 10 megabits per second. The remainder of the entries of our new array are obtained in the same fashion, with the only additional observations of note being that there are no paths from node C to node D, or from node D to node B, so we leave the corresponding entries empty. The last comment we'll make on this example is further justification for why an empty entry has an implicit value of 0. Since we're only considering non-negative bandwidths, 0 is the smallest possible value a link could be given. By being the smallest possible value, it's the identity for maximum, our stand-in for addition, and an annihilator for minimum, our stand-in for multiplication. This shows that 0 fulfills the same role as it does in the case of the usual real number plus and times. Using the same network, let's instead look at latency. Whereas the net bandwidth of a path is the minimum of the individual link's bandwidths, and we wish to maximize our net bandwidth, the net latency over a path is the sum of the latencies of each link, and we wish to minimize our net latency. Here we have an array representing the latencies of each link, and a striking difference from our previous examples of matrices and arrays is the fact that we've explicitly recorded zeros. What then is the implicit value of an empty entry? In our network context, an empty entry in the node X row and the node Y column represents that there's no link from node X to node Y. We may treat this scenario as a link which has infinite latency, further justified by the fact that infinity is the identity for minimum, our stand-in for addition, and an annihilator for plus, our stand-in for multiplication. By performing min plus array multiplication between the latency array and itself, we can calculate the net latency of paths between two nodes crossing at most 2 links. For example, from node A to itself, we may either stay at node A the entire time, a net latency of 0 milliseconds, or go to node B and then back, 5 milliseconds from node A to B, and another 5 milliseconds from B to A to give a net latency of 10 milliseconds. The minimum of these net latencies is 0 milliseconds, the value of the corresponding entry. Similarly, from node A to node B, the only option is to take the link from node A to B, which has a latency of 5 milliseconds. Whether we consider ourselves as staying at node A for our first step before going to node B, or going to node B as our first step and then staying at node B, the net latency is unaffected since staying contributes a latency of 0 milliseconds. From node A to node C, the unique path goes from node A to node B and then to node C, giving a latency of 5 milliseconds plus 2 milliseconds for a net latency of 7 milliseconds. The remainder of the calculations are analogous, and the final array is the result of performing our min plus associative array multiplication.